Hi, this is Solomon Olumba, and this is a presentation for my master's dissertation project. It's in partial fulfillment for a master's degree in data science from Becker University. Student number is C77333474. So I'll be talking about my project, which is the development of a network monitoring system for UAV swarms during BVLOS operations. So BVLOS operations have to do with operation of drones beyond the visual line of sight of the operator. That is in situations where the operator cannot see the drones, unlike traditional VLOS and line of sight where you fly drones and you can see them and the operator has some reaction time to handle certain things that happen with the drones. But in BVLOS operations, the drones have to be more sophisticated, better equipped, and have advanced communication technology for them to be flown in those settings where you don't have as much reaction time as you would in a traditional line of sight setting. So I just want to briefly talk about the scope of study and what's currently happening in the field. So there's been a drift in the use of UAV technologies. These days they are called drones, and from their initial military use, they are now being used for commercial purposes, and a lot of companies are trying to go into this area of research, go into this line of research, and they're investing a lot of money, a lot of resources, as we can see, and they have certain aims and benefits that they hope to get from investing in UAV technology. But the most important part of UAV technology is the concept of swarms. Now, swarms take the power of a single UAV or drone and multiply it by the total amount of power of drones that you have within a swarm. So if you had one drone for surveillance, and now you can have a swarm of drones that can be programmed, and you can have a group of 20 drones that can be programmed to go for surveillance. Likewise, if you have, that same concept in logistics and transportation, if you are a logistic company and you want to implement swarms to your fleet, you can have a single operator for 50 swarm for 50 drones in a swarm. You could have um, 10 operators for a much larger swarm of drones at different locations. And this will help to save costs business wise, the manpower you would need for hiring drivers, um, paying and maintaining delivery trucks, all of that goes away because these UAVs are just chargeable and they're electric. They emit zero carbon into the environment, so you're cutting your carbon footprint. And by doing so, by incorporating this technology into your field or into your business, you can potentially be reducing, congestion on highways. So if every company implemented this strategy towards business and say, oh, they're going to adopt heavy technology in their businesses, I believe we can achieve all of this potential benefits of UAV swarms. So during the literature review, we were able to identify some well-known problems within the field, which is the topology. So because of the swift movements of the drones, the network topology keeps changing. The challenges are also in weather and routing protocols, because routing protocols determine how data is being transmitted within a swarm of drones. So every routing protocol has its own unique advantages and disadvantages, and you have to make sure that the routing protocols and the mobility models go hand in hand and go together. So now I'm going to talk about the application itself, and I'll just go straight to it and illustrate what it does. So we've tried to represent a multi-layer UAV swarm architecture in here. And as you can see in the dashboard, we have network analysis that tells you the most connected UAV, that tells you the most critical ones, the roles of this UAV. So this is powered by graph technology, and all of this analysis is done using centrality graph matrix, betweenness, closeness, and degree centrality that tells you the strength of relationships within networks. And over here, we have the statistics of the network. So it's currently showing that the mean latency and throughput, the latency has increased drastically and the throughput has reduced as well. And the minimum battery of the fleet is 1%. So if you also go down here, you would see um, some analytic tools here where you can actually check the UAV numbers or UAV names. In reality, this would be different types of UAVs, and then you can get their data and then compare them to one another to see what the changes really are that are happening within the network. So this just allows you to let the data speak to you and tell you where things are going wrong or where to watch out for and what actions to take. So when you're in BVLOS settings, you don't have the opportunity to see what's going on and what's going wrong. But when you have a very good network monitoring system, you can get a message from the data itself. So we've created two possible simulation options here. One is to simulate a normal network. The other one is to simulate distributed denial of service attack. And we also analyzed how this network can indicate that. And as we've clearly seen here, to a normal drone operator, someone who is familiar with drones, they would know that this is the classic effect of a distributed denial of service attack. We can go on to check the targeted UAVs to see how their own matrix deviates from what we have within the swarm. And if I just close this here and wait for it to load, that's it. And we can see how the attacked UAVs increase dramatically in latency and then reduce in throughput, which is the amount of data they send among themselves, and how the battery drastically reduces. So all of this can point to a drone operator and give them that feedback and tell them, oh, this is going wrong in the network. You need to have a look at this and react to it. So we've also implemented anomaly detection um, on the drone data. So since we've already simulated the effect of a DDoS attack, I would just go right ahead to run the anomaly detection script to see how it behaves and the results we get. So running this, um, it's loaded, so we get a perfect accuracy prediction of anomalies in the data. So we've predicted 170 true positives and 34 true negatives, and we've not predicted any false values. This is what the scatter plot looks like. You can see how the model distinguishes anomalies from regular data points. You can also see the histogram of how this analysis was carried out and the scoring. You can see this clear separation between what are anomalies and what are not anomalies on the left side. And we can also see the precision and recall curve, and we can see that it's almost a perfect, if not a perfect line. So the model has performed excellently well to predict anomalies. So this project that is being seen running here, it just pulls all of this data from different sources. And to do this, we've implemented a graph database, which stores the properties of all the UAVs and which we can query in real time and ask to get what the minimum battery is for the fleets as they fly, and maybe get what the latency is, the smallest value of the latency is, and what drone it belongs to. We can monitor that status in real time, and we can also see how the data is being saved using MongoDB. So we've saved the network matrix data in MongoDB and the simulation matrix data in MongoDB. It's all in here. So what this application does is it just simply pulls all of this data from multiple sources. The graph itself is being pulled and created from the graph database, and we use the D3JS for that. And the rest of this data comes from MongoDB. So if we run any simulations, all of the data gets saved to the back end, right? And then when the simulation is over, it runs the analysis, calculates everything. It's been done automatically in script, and then brings the results. So I would have gone on to explain all of this, but a lot of these are very, very in depth. We have algorithms for simulation, simulate movement, to update the drone positions, to simulate the DDoS attack, to create routing mechanisms and algorithms. So, which is a very, very, which was a very, very key point to be able to replicate routing in this context. So that's what we've been able to do so far. So if you look here, you would see example of what the code, the last code that ran, the DDoS attack. If we look at the routing history here, we would see how the latency for each path that packets are delivered to for the targeted UAVs, how it increases dramatically, and how it also affects the overall performance of the network itself. You see that packets are not getting delivered at all, and you can see that the latency is dramatically high. So all of this points to how data can drive decisions when you're using applications like this. So this is how we can use graph technology, use web applications and web technologies to develop sophisticated systems like this. Future directions will be to develop this, model it, and test it. So I hope I've been able to offer some sort of education to people who are new in the field, and I hope I've done a very good work presenting this to you. Thank you very much for your time.